Welcome to today's webinar. The topic today is linear stability analysis in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today and will answer your questions together with Sonja. My colleague Jonas will do the presentation, but my two colleagues can introduce themselves.
Yeah, of course. Good afternoon. My name is Jonas Bien. It's a pleasure to have this presentation for you today. I'm working at Dlubal Software as a product engineer and also doing some customer support, and I'm responsible, amongst other colleagues, for the structural stability add-on and steel design. So that's what we will focus on today.
Hello, my name is Sonja von Bloh. I will answer your questions today.
Okay, thank you for your introduction. Then we can switch off our webcams so the attendees can see the full screen. For the attendees who participate the first time, I explain how you can ask questions. You can show the control panel with that arrow, and then you can enter a question here and we will answer you. Yeah, you can also watch the entire webinar and then email questions to info@dlubal.com. Yeah, if you don't get an answer during the webinar, maybe there are too many, you will get an email afterwards. Okay, that should be all from my side. I hand over the screen to Jonas. Jonas, it's your turn.
Yes, let me quickly share my screen. Could you give me some feedback if it works?
Yes, that's fine.
Yes. Okay, so you should see my table of content now. Yeah, thanks Andreas for the introduction. Within this webinar, I want to show you the linear stability or bifurcation analysis that we can use in RFEM 6 as a tool to assess structural stability. And yeah, I want to show you how to use this tool and where it is used internally in the background to assist the design of, for example, steel members. I would like to demonstrate this on some smaller example models that I have mostly prepared before. So we will jump into more or less finished models instead of focusing on the modeling of more complex structures. We will do that maybe next time again. And the table of content looks like this. So first I want to focus on the stability analysis of members and frame structures. And the second step, I want to go to the stability analysis of on a cross-section level using the finite stripe method. Then I want to show you how the buckling analysis is integrated in the steel joints add-on. And lastly, I want to show you how we can use the add-on structure stability for troubleshooting of instabilities, how we can leverage that in this for that purpose. I think Andreas missed the point of mentioning that we have a lot to discuss today. I have prepared a bit too much. I realized that when I did the first webinar on Tuesday. So I will roughly, or it will roughly take me 90 minutes to go through this. So I hope you have enough time. If you don't, then it's no problem. We will, of course, record the presentation, and you can watch the rest then on YouTube on our site. You will find the recording. All right. So apologies for that. Okay, before we jump into the first model, I want to give you a brief introduction and explain at very least a few points that are related to the stability analysis and how we perform it in RFEM 6. So what elements or structures are we taking care of with this analysis method? It's usually slender members and structures under compression that tend to become unstable, where the slenderness of a member or a structure is not only defined by its dimensions, so the greater the length of a structure or member compared to the cross-sectional dimensions, of course, it's more slender and prone to instabilities, but it's also related to material properties. So if I have a material that has high strength and low stiffness, then it's more likely that stability failure will be the critical design element as opposed to cross-sectional failure. And then lastly, the boundary conditions, of course, play a major role. If I have rotational restraints or lateral restraints for our member, it's not that likely to become unstable. And what do I mean with unstable? When we reach the unstable state, we have no clear state of equilibrium. We have instead a bifurcation of equilibrium. So there are multiple paths that the structure may follow. And yeah, that's why this linear stability analysis is often referred to as a linear bifurcation analysis, or LBA. I might use that abbreviation along this webinar as well. And also the critical load may also be named sometimes as bifurcation load. Using the FEM, the ideal bifurcation load can be determined solving a conventional eigenvalue problem. So we can set that up and solve that. In that context, what does ideal mean? It means for the stability analysis that we treat the structure as linear. So we assume a fully linear structure behavior and a perfect geometry. So the base geometry of our model is used in this stability analysis. The eigenvalue problem in the general formulation has two symmetric matrices, A and B. The eigenvalues lambda and the respective eigenvectors x. And to solve for the unknown eigenvalues lambda, we have to set the first term of our formula to 0, and that's mostly done by calculating the determinant of this first part in the bracket and set it to 0. And yeah, we have multiple numerical tools or solver to do that determinant determination. Yes. And in our specific case, in the stability analysis, our two symmetric matrices are represented by the linear stiffness matrix and the geometric stiffness matrix. The geometric stiffness matrix is dependent on the loading conditions. That's also why we, before we can solve a stability analysis, we need to perform a structural analysis to determine the internal forces in the system and to determine the entries in the geometric stiffness matrix. The eigenvalues are named critical load factors or bifurcation load factors in the context of the stability analysis, and our eigenvectors are the mode shapes, which are somehow scaled deformations of our model. We want to start with some fundamental solutions that are very well known amongst the civil engineers. So Euler already in the 18th century provided some simple analytic solutions for prismatic members under pure compression. They are well known as the Euler cases. I have listed the 4 fundamental cases here with the analytical formulas to calculate the bifurcation load or the critical load. In the first step, I want to go into our program now and try to simulate an Euler case 2 and make a small comparison if we can evaluate the correct critical load according to Euler and what else we can get from this from our structural stability analysis. So let's jump into the program, and as I said, I have prepared some smaller models for you. The first one is this simple Euler case. I have an HEB 300 beam with a length of 5 meters, and I applied a unit load of 1 kilonewtons that sets the member under compression. In order to perform a stability analysis with our add-on structural stability, I need to first activate it, and I can find it in the base data of the model. I activate the respective add-on here, which you can find under analysis add-ons, click OK. And as soon as I do that, we have the options to activate structural stability analysis, or this critical load calculation for a specific load case or for load combinations. So now I open this load case where my 1 kilonewton is applied to the column head, and I activate the calculation of the critical load. I have then a type or a general setting for this stability analysis that I can of course change. So in the stability analysis settings, I can choose which method I want to use for the critical load factor determination. In this webinar, we want to focus on the linear stability analysis, as I said before. If you want to learn more about the incremental method, you should maybe watch the last webinar, which I held together with Andreas Hörold. So there we focus on this method. But today we want to just keep it linear, apply the eigenvalue method. 4 eigenvalues are enough for our simple case, so I keep this number set here. And then we have these multiple solvers variants to solve the determinant of our eigenvalue problem. But the default solver should mostly suit us in this for this problem. There might be cases where you have subsystems that are not connected to each other. Then this default solver will throw an error and suggest another solver variant. But with this default settings, I can just run the load case, and now the first thing the program is doing is that he solves the static analysis, and then he solves for the stability analysis. And when I have performed the stability analysis, I not only get the results for static analysis, but I can also switch to the stability analysis results by this drop-down menu here. Okay, so what do we see here? First of all, we get a drop-down menu here in the upper left corner, and also in the table we can see that we have these 4 mode shapes calculated with a respective critical load factor. This represents the factor which I can multiply the external load with until my system would collapse due to instability. So if I would increase the unit load of 1 kilonewton up here up to 7,035 kilonewton and run a second order analysis, my system would become unstable and I would get an error message saying me that. So I can read these critical load factors here. Then we have also a magnification factor, which is also known in steel construction as the Dischinger factor. It can, in some cases, be utilized to calculate internal forces according to second order theory by just multiplying this magnification factor to the first order internal forces. That's not commonly used, but I just want to highlight that this is the magnification factor because it's denoted with the parameter alpha. And in some other cases within our program, you will find that the critical load factor or the bifurcation factor is denoted with this alpha parameter. So just that you are not confused when you see this parameter in another context. Okay, so we can go through the 4 eigen modes here by clicking the table entries, or also go through the entries in the drop-down menu. And we can see the first eigen mode that is presented to us would resemble buckling of our I-beam around its weak axis. And it's doing that in a symmetric way. We have simply supported beam here, so that looks like expected or as expected. Then the second mode shape would be buckling around the strength in the strength axis. And the third and fourth eigen shape or eigen mode They are some multi-wave eigenmodes for buckling around the weak axis. These are mostly not very interesting for us, so usually only the mode shape with the lowest critical load factor is of interest for us. And I want to know now, compare the critical load factor that we have calculated here with the critical ideal Euler load that we have for our Euler case 2. Just so that you remember, we could calculate it just using this formula, pi to the power of 2 times the Young's modulus times the moment of inertia of our section, and divided by the effective buckling length. In this case, it would be the length of our member times 2, or to the power of 2. And I could do that using my calculator, but I can also, but then I would need to look up all the values for my section, the member length, the material properties, and so on. So I want to show you an alternative solution. We can also use the in-app console that we can open via the toolbar. And in here, I can reference like all the objects that I have in my model. For example, I could reference my material number 1 by typing this and then typing a dot, and then I see all the options or all the objects that I can, or the properties that I can ask this object for. For example, I would find the elastic modulus here, and if I press enter, then I get as an output the elastic modulus of our material number 1 in SI units. So that's important. And of course, I can do some more complex calculations here. I could now like take this elastic modulus here, multiply it with the moment of inertia of my first section. Let's see first what the critical Euler load would be for buckling about the weak axis. That's what the mode shape 1 gives us. So I use the moment of inertia for the z-axis here in that expression. Then I multiply it with pi to the power of 2 and divide it by the length of the member. This is member number 1. You can also assess this here. And of course, I have to also square this. And if I hit enter, now we get the result for this formula as 7,100,000 Newton. I need to divide it by 1,000 and I get the result in kilonewtons. So that's pretty close to our critical load factor that we calculated here according with our structural stability add-on. And the difference is now comes from an effect that we take into account in our with the finite element method in our calculation, which is the shear stiffness of the section that was neglected by Euler. So if we want to compare values, we can manually deactivate the shear stiffness for our section in RFEM and do the calculation again and see what our critical load factor would now be. And if I again go to the results, we now see that our critical load factor is much closer to the ideal Euler load. It's really it compares very, very well. So we could, of course, also calculate the critical load for buckling around the strong axis. Just we need to swap the Z with a Y value, and we have the moment of inertia about the strong axis, and also this value is quite satisfying if we look on, or with regards to our result that we received from the structural stability add-on. So that compares quite well. We've, as we expected, met the results of the analytic formula. Okay, now that that's set and we are confident that our solution here provides reasonable values, I want to show you another important result of our stability analysis when it comes to member results. And we can, because it's often used for the later design of the column, if we, for example, would take a classic approach to design this steel column using an equivalent member method, we would need effective buckling length. And we can use the structural stability add-on to calculate the effective buckling length for this equivalent member method. Therefore, we just go to the results by member tab in the table and go to effective length and critical loads by member, or the last tab is also has this effective length values included. And now we see for each mode shape, we have effective length given for both main directions. U represents the strong axis, while V represents the weak axis. It's like Y comes before Z and U comes before V. That's one way to keep it in mind. But now we have for the first mode shape two effective lengths for both sides, for both axes. And I want to explain what is done in the background. It's nothing else than taking the critical load formula from Euler for case number 2 and recompose it or evaluate it for L, with beta being the buckling length coefficient and beta times the system length being L critical, so the critical buckling length. And when we know what our F critical is, so the critical buckling load, then we can evaluate the critical buckling length. And of course, we can also, when we divide it by the system length, we can evaluate the buckling length coefficient beta as well. And that's what is done here in the background. The critical load of the member is just the normal force, or the actual force in the member times the critical load factor. And from this F crit, our effective length is calculated, and then the effective length factor is calculated. And we can do that as well using our console. So we can also plug in this reassembled formula here as well. So I have L crit and I have here F crit. So that would be the parameter for our critical load. And now I just need to, if we want to have the buckling length for buckling around the weak axis, I again evaluate the F crit formula with the moment of inertia for the weak axis, and now I can calculate L crit with this F crit value, and what I get from the formula is a length of 5 meters, and that's exactly what we get here as an effective length for buckling around the weak axis. Now we have to take care or be a bit cautious. If we would take the critical load for buckling around the weak axis and evaluate the effective length for the strong axis, that would be, it would just be wrong. So if we would take this effective length factor for the stability design with the equivalent member method. So when we want to extract these effective length values for our design, we have to take or make sure that the mode shape that we are analyzing fits to the effective length that we are reading. So for example, for buckling about the strong axis, we should definitely take the second mode shape and use the critical length factor given for the u-axis here. So I can demonstrate that, just simply by again evaluating the L-grid formula, but instead of taking the z moment of inertia for the weak axis, I put in the moment of inertia for the strong axis, and I received this value of 8.57 meters, but it wouldn't correspond to the relevant buckling length of our system for buckling around the strong axis. So this is very important to keep in mind when using these effective lengths for the stability design. Then one thing I want to show, we can directly import these buckling lengths into our design add-on. So if I want to design this column here with our steel design add-on, and I want to do it with the equivalent member method, I have to assign these effective lengths. And here I have the option to import the buckling length from the stability analysis. And if I click this, we get another tab where I can enter the load case and the mode shape and the member number. And now it would take this buckling length coefficient from mode number 1 for beam number 1 and evaluate the effective buckling factor and use it for the design. In this case, we have to take care that buckling around the strong axis happens in mode number 2, so is observed in mode shape number 2. So we would need to enter mode shape number 2 here, and mode shape number 1 would be for the buckling length coefficient for buckling around the weak axis. So that would fit and suit our expectations. Of course, we can do that for more complex systems as well. We just need to make sure that, or have to keep in mind that when we have a more complex system and we change something, then the order of the mode shapes can also change. They are always sorted in the for the lowest eigenvalue or the lowest critical load factor. So the mode shape with the lowest critical load factor is always mode number 1. And if we change something in our system, it can happen that this sorting changes. But here these entries then need to be checked again because they are not smart or know how to adopt to the changed model. So we would do that manually. So that we need to take into consideration and always keep in mind. So sometimes it's just better to do the stability analysis and then manually put in the buckling length coefficients here, and we don't need to make any thoughts about it anymore. All right, but that's not what I want to focus on now. I want to show you instead how the buckling length coefficients, of course, change or adopt when I enter or when I adjust the statical system. So when I, for example, take a rigid boundary condition at the member at the bottom of this column, it should, of course, now calculate a lower buckling length coefficient because now the system resembles Euler case number 3, and we know that here we would expect a buckling length coefficient of 0.7, and that's exactly what we get for the first mode shape for the weak axis and the second mode shape for the strong axis in this case. Then we also need to take into consideration that, for example, or let's say for these cases, of course, why should I use my my add-on here? Because these cases are known. I can just apply the Euler formula and calculate my buckling length. But what if we have something like a spring stiffness here, a certain spring stiffness, which means that I'm with a stiffness somewhere between Euler case number 2 and Euler case number 3. And here it's not so obvious what the buckling length for our equivalent member check would be. Of course, we could look into textbooks also to that have these cases covered, but also here we can use the structural stability analysis to evaluate the effective buckling length factor here. And as we expected, it is between 1 and 0.7. So everything's set. Because it's a linear analysis, we need to, or it is interesting what the program does with nonlinearities. So, for example, if I apply some kind of nonlinear boundary conditions here, which at the first glance don't look that nonlinear, because in this case I want to apply a stiffness diagram where I have the stiffness of our spring at the column bottom in relation to the vertical load, but it, as you can see, it should be constant, and no matter what the vertical load in the column is, the spring constant should always be constant. So it doesn't look nonlinear at the first glance, but we have to take into consideration all these nonlinearities are ignored in the structural stability analysis. So I want to just demonstrate this. So although we have set this nonlinear spring stiffness at the bottom, we as a result here get the Euler case 2, where a pure hinge is assumed at the bottom. So only when it comes to the supports, only these entries are taken into consideration for the structural stability analysis. All right. Of course, when we are working with other nonlinear elements such as tension rods or buckling members, then these are taken into consideration or not according to their state in the structural in the static analysis. So if we have a tension member that is under tension, it will be taken into consideration in the structural stability analysis as well, and vice versa. Okay, then one last thing to finish this simple example here. Let's delete this nonlinearity and see what happens if we divide this member in half. I just introduce an intermediate node and divide these one column into 2 separate members, and again run the structural stability analysis. What does it do with the buckling length? Is it still valid, or does it give me some weird results? Let's see. The critical load factor is still the one, or is the same as if we would take wouldn't have divided this column. And now the buckling length, or to dock it again, the effective length of our members is also the same. So now we have two members, but the effective length for each member is still 5 meters, and that's what is expected when we again look at the formula for the calculation of our critical buckling length, because the Young's modulus, or the moment of inertia, they have not changed, and also the critical load factor has not changed. The only thing that changed is our reference length L for the member. It's divided into half, and that is then only visible in the buckling length coefficient, which is now 2 instead of 1 for each of the members. So we could still use this effective length factor for the stability design within steel design, or some design add-on. It would still be valid. Okay, now let's jump into, or increase the complexity a bit. So what if we have more than one member in our model? So in this case, we have a 2D model of a two-hinged frame with an additional column number 5, that is just connected to this 2-hinged frame by a truss member. So this is basically a simply supported column, just as we have seen it before, which leans toward this 2-hinged frame here, or is supported by the 2-hinged frames at the column head. All 3 columns, so member number 1, 3, and 5, are loaded with a load of 1000 kilonewton in compression. And now let's perform a stability analysis for this load case as well. It should be all set for this analysis. So same settings as we have used them before for the Euler case. And accordingly, we also get 4 mode shapes for our structure. And I want to quickly browse through these mode shapes together with you. So the first one is some asymmetric lateral deformation of the 2-hinged frame, and also this connected pinned column is also moving with the 2-hinged frame. Then the second mode shape would represent buckling of the longer column with the pin supports around the strong axis. The rest of the structure does not seem to have any deformation. And the third would also be a higher mode of this pinned member number 5. And mode shape number 4 would resemble a symmetric buckling mode of the 2-hinged frames without any participation of the simply supported column here at the side. So if we want to now extract the effective length, for example, for the columns here of the 2-hinged frame, we can again go to the member results of the stability analysis and check the effective length by member, and I can then click on one of those members, and I will automatically be routed to the respective table entries. And now in the first mode shape, as we have seen, this 2-inch frame suffers from buckling around the strong axis, and we could read the effective length factor accordingly for the strong axis in this column right here. So we would get an effective buckling factor of 2.8, which is also in the realm of the expected results for such 2-inch frames. If we now neglect this simply supported column here at the side, we would expect some effective buckling factor of higher than 2, and the exact value would be influenced by the stiffness of the girder and the columns, and of course the length and so on. Now with the additional column, it's also influenced by that. So that would be quite clear. So we could take this effective length factor for designing this column for buckling around the strong axis. But what about the column number 5? Because in this first mode shape, the column is also deforming, or it seems to be deforming. And when we look into the effective length factor that we would evaluate for that case, we would get 1.25 times the system length. And that would be a bit strange, because I would say when I design this and it's pin support at both ends, I would assume that this is designed for the Euler case too. So I would assume a buckling length factor of 1. And in fact, when we look a bit closer, we can see that the column has no local deformation. It's just rigid body motion at the that comes from the 2-inch frame. And we have a new tool to more objectively classify it as rigid body motion, because when we look at in the last column, we have this MRF value, the mode relevance factor, and this is a measure that takes into account the internal deformation energy of each member in each mode shape. And if we investigate the mode relevance factor for member number 5 in mode shape number 1, we see that there's no, we see that the factor is 0, which means that there's no internal deformation energy in this member, which means that it's just rigidly moving with the rest of the structure. But it has no influence on the mode shape that we are investigating, and vice versa. So this member has also no influence on the structural stability of this 2-hinge frame. And if we want to look for a mode shape for this particular member that is relevant for the buckling length determination, we would need to look for mode shapes where our mode relevance factor is higher than some value, maybe higher than 10%, 15%. That's a bit up to engineering judgment, but definitely not 0%. It's a relative measure because deformation in a stability analysis are not absolute values, but they are somehow scaled, and so is the mode relevance factor. So you can imagine that the member with the highest internal deformation energy has always, in the model for one particular mode shape, has a mode relevance factor of 100%, and acts as a reference member for all the other members. So in the first mode shape, we have 3 members that have a mode relevance factor that is significant, so 78% or 100%. And then we have 2 members, this truss member up here and the member number 5, this pinned column, that have a mode relevance factor of almost 0. In the second mode shape, we see that only member number 5 has a mode relevance factor greater than 0. So we see that in this mode shape, only or the stability phenomenon or the instability in the model is quite localized. So that is also what the mode relevance factor can tell us very quickly. So when we browse through the modes and we see that only one of the members has a mode relevance factor that is significant, then we can already tell that this is a very localized stability issue. We can, of course, also use the filter function to make our lives a bit easier when browsing through this. For example, we could say that we are only interested in members that have a mode relevance factor greater than 20%. And if we do so and now go through the mode shapes, we see, okay, for mode number 2, we have only one entry that should be a localized stability phenomenon and not so much related to a structural failure of the whole structure or substructure of the model. So that way we can use the mode relevance factor to somehow filter mode shapes for our purpose. For example, for the determination of effective length factors. Because here I would go the other way around. I would, when I'm interested in the relevant buckling factor for column number 1, I would go through the modes for that I have calculated and only take into consideration the mode shapes that have a mode relevance factor that is significant, and read my buckling length factor then from the mode, or take it from the mode that has the lowest critical load factor. In that case, I would definitely take the value of 2.8 meter for column number 1 and also for column number 3. All right, but I want to show you in the next step how we could also leverage this tool in a more realistic setting, or how to approach the buckling length determination in a more realistic model. So here we have a industrial hall. We have a lot of different load cases here that of course would give us some I don't know, probably about 100 or 200 load combinations. Of course, in some applications, we can have a lot more load combinations. And then the question is which load combination, or the first question for our buckling length determination is which load combination is most severe for buckling for a specific member. And I have now, for this case, deliberately started with result combinations, because sometimes, for example, when I want to design bridges or so, I may have 10,000 load combinations, and it's not possible to calculate all 10,000 load combinations and assess them for stability. So what I would recommend you, if you have too many result combinations to handle it in one model, of course here it would be still feasible and no problem, but for if you have additional load cases, that can be a problem. I would, in the first step, calculate my combinations with result combinations to get the envelope of results. I need to calculate, yeah, the design situation where all the complete envelope of all result combinations is given. And then I would see, for example, when I want to design the columns for buckling, I would look into the internal forces that I get in this envelope solution, and I would look for the most critical ones for buckling, and that would of course be the combinations that give the highest compressive load in the columns, and I can find those if I go to the static analysis results for this design situation, go to results by members, internal forces, and then let's stick to this middle column here. I would click the column and I get in this result combination all extreme internal forces for this member. So for example, I get the combination of internal forces with the lowest or with the highest axial load, including the sign, and the lowest axial load. And the same would be printed out for the highest shear force in Y direction, highest shear force in Z direction, lowest shear force, and so on. But we are interested in buckling, so I would be interested in the combination that gives the highest compressive load, which would be this one here with the minus 116 kilonewton. And in the last column here, I would have presented the loading or the load combination that leads to this axial load. And now from the result combination, I can just by right-clicking this combination, I can generate a load combination just from this table. And now for this load combination, where I have the feeling that this could be the most relevant for buckling of our columns, for this load combination, I can now perform an eigenvalue analysis, so a linear stability analysis, by just activating it here and calculating it. So now I very specifically run the stability analysis for just this one load combinations that I have generated from the envelope. And now the second question, after we have sorted the first question, which design situation could be relevant, I would now have to figure out, okay, for this column, which mode shape is the most relevant for the determination of my buckling length. So again, as before, I have now 20 critical load factors and mode shapes, and I can of course browse through them, and I see some of them involve like some deformation or buckling of the frame where this column is involved. Some of them are only like some isolated buckling of those columns here, or some compressive member in the roof. So these wouldn't really interest me. And in order to filter these out, I can again use the mode relevance factor. So I just go to the table effective length and critical length by members. I click on my member number 4. I get the whole table here. So I get the mode relevance factor for all 20 mode shapes that I have calculated, and I see that only in 2 of these mode shapes my column member is really participating in this mode shape. So these would be the only 2 mode shapes that would be suitable for extracting the buckling length. I could, of course, again apply the filter to make it more accessible. And then I would again follow like the rule from the last smaller example, that I take the mode that has the lowest critical load with a significant mode relevance factor, and take the effective length factor for, in this case, buckling around the strong axis from this mode shape. So this is how the mode relevance factor can somehow help you to assess the relevant mode shapes for a particular member design. Yeah, that's what I wanted to show you on this model. And now I want to go or take the next step and highlight a thing that you may have noticed so far. We have only discussed the flexural buckling of members, but especially in steel structures, other stability modes can also govern the stability design of these members, namely torsional buckling or flexural or lateral torsional buckling. And we can also take those into consideration or investigate those stability modes with our structural stability add-on, but we need to activate warping torsion in order to be able to detect those stability modes. And I want to make another small example where we just investigate the lateral torsional buckling of a simple system, where we again, as in the first Euler case, we know the exact solution, and I want in the first step compare the values that we are getting from RFEM with the analytical value. So in order to perform a structural stability analysis where we can also consider lateral torsional buckling, for example, we would in addition to the structural stability add-on, also require the torsional warping add-on. And as soon as we activate the 7th degree of freedom, this would be directly included in the stability analysis, or would be taken into account. And I have now for this simply supported member here, it's an HEB 300 again, with a length of 10 meters and a constant bending moment. I could again run the stability analysis, and now we are not only getting modes for flexural buckling, or we wouldn't get any flexural buckling modes for this member at all because we have no compression in it, but I didn't activate the structural stability analysis for this particular load case, so I will just do that. And now we should get a lateral torsional buckling mode. When we switch to the results of the stability analysis, we can now see very clearly this characteristic deformation of our member. It tilts and at the same time moves in the direction of the weak axis. And again, we get a critical load factor. And this one we can compare with the analytical solution. For this simple system, an analytical solution can be easily found in the textbooks. It was once also implemented or written down in some of the codes. For example, in the old German steel construction norm or code DIN 18800. I think in some national annexes of the Eurocode 3, it's also given this formula. But for our convenience, I already plugged this formula to calculate the critical bending moment for lateral torsional buckling into our global parameters. So that's another thing I can do instead of just using the console and typing in my commands to evaluate certain parameters or values. I can also use global formulas to global parameters to calculate something. For example, I have now created a formula for the evaluation of mcrit, and we can look in what goes into it. Maybe this looks somehow familiar to you. So here we have a value or a parameter that describes the moment distribution, which is zeta. It's 1 in this case for this simple case with uniform bending. Then we have the elastic buckling load, mcrit. That's the one that we already assessed in the first example. Then we have some parameter C that takes into account the warping and torsional stiffness of our section. And we have the ZP, which resembles the eccentricity of the loading, which is in this case not important. And what we get from this formula is a critical bending moment of 574 kilonewton meter. We could also use the console again to evaluate this. So all the global parameters that we have stored, we can call them here in our console. And this, in this case, it's again written in SI units, so I would need to divide it by 1000 to get to kilonewton meter. And this is very close to the value that we evaluated here with the structural stability add-on. So it works again quite well. But of course, as in the Euler case, we can use our structural stability add-on to investigate much more complex cases. For example, we could add member support. So I go to the member and add a support, and then I get this tab here where I can enter a member support. I could manually put in some rotational restraint. I could even apply an eccentricity of this member restraint. For example, I could say I have a rotational restraint at the top of the flange. And we can now also in the global analysis take into consideration shear panels and rotational restraints. So these are also, they are entered as fictitious stiffness. And you may know them from steel design or aluminium design or timber design, where you had always access to those restraints, and they were only considered in the design of the member, so in the design add-on. But we can now use them in the global structural stability analysis as well. So I could, for example, define a rotational restraint. For example, I want to consider some kind of sheeting that I have on top of my girder. I will now just take some random settings, more or less. I take some sheeting just to get some stiffness. Of course, these values, they were accessible all the time, but now we can, as I said, also leverage or use the stiffness that we define here in this global structural analysis. And one thing that is also new, and I want to highlight to you, is that for the spring stiffness of the connection between the trapezoidal sheeting and our member, and also for the load introduced to the sheeting, we can now set load dependent values. So if we click these options here, we can, or we could, if we had multiple load combinations that we would like to investigate, we could set different values for different load combinations to for example, distinguish between situations where we have suction on the roof and compression or pressure on the trapezoidal sheeting. We could take this into account by adding different values here in the table. This is also quite new since a few months. And with this rotational restraint, I could also add a shear panel. And by the way, we can also are now able to not only add a shear panel in Y direction, we can also add a shear panel in Z direction, which could be interesting for columns that are also girders that are for some reason rotated by 90 degrees. So we can also use that now in the since some weeks, and we have now calculated directly some stiffness for the rotational restraint from our trapezoidal sheeting, and we could consider this in the stability analysis to take it into account. And in our, or by, let's say, put it that way, by default, these fictitious stiffnesses, so the trapezoidal sheeting in this case, would only be accounted for in the design add-on. So if we activate the steel design add-on, for example, in this case, because we have a steel girder, and I now activate the lateral torsional buckling check according to the equivalent member method, we already see here that the default way of calculating the critical moment value is using the eigenvalue method. So the method that we also use in this structure stability add-on. Of course, we need to set some boundary conditions here for this for the design add-on. But in our case, it's quite simple. We have simple support with fork supports, and that's what the default settings are also for the effective length settings. So that should be all right. Okay, in order to perform the steel design, we also need a design situation and some load combination inside this design situation. I will just add a load combination with 1 times the first load combination. And if we now do the calculation, so we are now running a static analysis, then the structural stability analysis of this member, and then the steel design analysis. Let's check the results and compare them. So first, in the stability analysis, it seems like nothing has changed. So we have still a critical moment, bending moment of 574 kilonewton meter. But in the design add-on, let's check the result here. We have now the check for lateral torsional buckling here. We can also see what the relevant mode shape would look like if we click on this design details. And if we double click on the design details, we can also check what is mcrit, or what value for mcrit is evaluated in the internal eigenvalue analysis. And we see that now in the steel design add-on, the rotational restraint on top seems to be already taken into consideration, because we have a much higher critical moment in our steel design add-on, while in the structural stability analysis, the values stayed more or less the same. But we have now the option to take these fictitious stiffnesses into account also in the structural stability and static analysis. And we can do that by adding a structure modification to this load case. And here we just need to activate the option to consider shear panels and rotational restraints also in static, stability, and modal analysis. So before, it was only possible to take these shear panels and rotational restraints into account in the design, so in the LTB design within the design add-ons. But now we also moved this possibility to the global analysis, because you may want to perform a lateral torsional check, like using a second order theory analysis with imperfections, and maybe you want to also have these rotational restraints be effective in this like global analysis in this matter. So that's why we added this option through the structural modification. What is also new is that you find these objects, so the member shear panels and the rotational restraints, now under types for members and not anymore under the types for the design add-on. Like in earlier releases, we had those two objects under, for example, the types for steel design or aluminium design or timber design. Now you find them under general objects for types of members. Okay, so that would be also one example on how to evaluate those other failure modes of typical beams with our so how to like analyze all of these typical stability modes of beams. But we can even go further and say, okay, when we like do this calculation with our beam models, we of course always assume that the cross section stays rigid and there are no cross section deformations with respect like to the stability analysis. And of course, we can also we could now, if we are interested in local buckling of the cross section, for example, we could of course extract from these beam models a shell model that is quite easy in our software. You can just like right click on a beam member and say I want to generate a surface model from this member, and then surfaces are directly generated with the correct thicknesses, just as they had the thickness for the member. For example, the top flange would already have a thickness of 19 millimeters that would correspond to the HEB section. And now we could mesh this in a very fine sense to do a stability analysis for this shell model. And in this, or by doing so, we could also analyze local buckling modes of the section. And because it's not very interesting to do it with a hot rolled section that is in this case not susceptible to those local failure modes, I want to do it with a cold formed thin walled section. So here I have prepared a fifth model where I have a parametric C section with a height of 200 millimeters, width of 75, and a wall thickness of 2 millimeters. So that would be a perfect example for a thin-walled, cold-formed section. And I have, as I just have shown you, transferred my beam model into a shell model. I have meshed it very finely in order to get all the relevant local buckling modes. And then I have for these I have modeled 4 different members with different length. So I have a very short element of this C section. Then I have one which has doubled the length, one with a length of 90 centimeters, and a very long C member as a shell model. And I have applied some boundary conditions that avoid any unwanted singularities in the model. And then I have applied in 4 different load cases unity load to the top and the bottom of these column stubs. So as in the first step, that should resemble the Euler case. So I have a beam with a certain length and I apply uniform pressure on it. But in this case, of course, I have a monosymmetric cross section, which is very thin. So let's check out the results. What do I get from such a stability analysis? Now in this case, I have performed a stability analysis of the shell model. And if we look for the results of the longest segment here with this 3.7 meter long C section here, I have the first critical load factor at 84 kilonewton, and I can see that the mode shape resembles flexural torsional buckling in this case. So in this case, I don't see any like buckling, local buckling of the different cross-sectional elements, but the whole section is deforming at midspan. If I check the second mode shape, I have buckling about the weak axis. Third mode shape now would be one that involves also local buckling of the web. And this we can only see like in with such refined shell model. Now what happens if we take a shorter column? Now we see that the behavior or the critical load factor or the critical mode shape is governed by local buckling. So in this case, our global buckling, like flexural torsional buckling or flexural buckling, wouldn't be the major issue, but stability failure would be more related to local buckling of the web. And I can go through this and I find several mode shapes where especially my web buckles in different configurations. And then in mode shape number 13, I find also a mode shape which is particularly interesting for code formed members, and that is distortional buckling. So in this case, not like separate elements of the cross-section deform, but the whole cross-section bends up, so to say. So if we look at the midsection, the lips are deforming horizontally, and at the same time, the web is also deforming. And then finally, for the very short configurations, I again find the local buckling modes. And what is also important to note is that the critical load factor is not changing significantly. So the first or the most relevant critical load factor is not changing a lot when we compare the three like smaller column segments here. We are always around 90, a factor of 90. But of course, this type of analysis comes with a drawback. It's quite cumbersome to prepare this kind of model. We see that we require quite a fine mesh to get valuable results, and calculation in this case would take like 1 or 2 minutes for these 4 cases here, because these are quite a lot of elements and degrees of freedoms that we need to solve. But we have also another alternative option to investigate such failure or local instability modes on the cross-section level. And this is kind of hidden in the edit sections dialog. That's why I want to show you that and highlight that we have this feature. So for a particular section, we have on the right side this preview of the section with all the dimensions and so on. And below that, we have a drop-down menu where we can find a lot of interesting features and functions of this cross-section. For example, unit stresses under certain loads. But right at the bottom, we also have the possibility to investigate the buckling shape of this section for some unit loads. For example, for a 1 kilonewton compressive load or for 1 kilonewton meter bending moment around the strong axis and so on. And if we click on that option, I can see that I get a diagram as a result. And what I get here is the so-called signature curve for our cross-section. And it gives the relationship between the critical bifurcation factor for this unit load, 1 kilonewton compression, in relation to the member length. So we can see that for like in the start, we have a very low member or small member length. In this case, for example, the first minimum is evaluated for a member length of 14 centimeters, which would be the smallest column stub that we have just investigated with our shell model. And when we look at the respective bifurcation factor, we see that it's around 90, which does very well correspond to the linear bifurcation load that we have received from the stability analysis on the global level in the shell model. On the right side, we can also see how the cross-section deformation would look like in this particular mode shape. And we can go along this signature curve and investigate like the different mode shapes that would be critical for a certain buckling length. So for a member length of around 90 centimeters or something, we would see this distortional buckling mode where, as I described earlier, we see this bending of the whole cross-section. And when we go even further, we see that the cross-section deformation is governed by rigid body motion, which resembles global buckling again of our cross-section. So that would again indicate that there's some kind of flexural torsional buckling that is decisive for the stability of this particular cross-section or member with a length, with a specific length. And we have also like the possibility to differentiate between these different failure modes here. So between local buckling, which is characterized by the displacement or deformation of single cross-section elements, for distortional buckling, which is characterized by a bending deformation of the whole cross-section or of multiple sectional elements. And then we can also get the global instability curve, where you can see the bifurcation load decrease significantly with increasing member length. So when we click here, we get all the like global instability failure modes that we would receive from a beam model. And one newly added feature is that we can not only display the results of the cross-section, but we can also directly like investigate the deformation of our member with a respective length in 3D. So, and this is of course also refreshed if I click one of those points in our on our signature curve, I get the respective deformation of a member of that particular length. And what happens in the background? So as soon as I start this feature here, in the background, the finite strip method is employed, and I want to show you what that means. Because as we have now already discussed, we can do stability analysis of beams, which has the advantage that we have very few degrees of freedom. Or we could also investigate stability of members with our shell model. But here we have a lot of degrees of freedom, and solution takes quite a while. And the finite strip method is some kind of intermediate accuracy solution where we divide the cross-section into multiple strips, and only one strip or element is used over the length of this member. And when we activate the finite strip method in the edit section dialog, a lot of these FSM members are generated, and the eigenvalue analysis is performed, and the eigen shape is stored, and also the critical bifurcation load is stored. And this happens on the go. So if we click it in the edit section dialog, it's done, and it finishes for like 50 analysis within less than 1 second. So this is quite a nice advantage of this analysis method. One drawback is against, like if we compare it with the shell element, that we can only investigate, at the moment we can only investigate specific boundary conditions. So the results are only valid for a simply supported beam that is assumed in the background. We can only assess results for unit loads at the moment, and we cannot like account for any local load introduction. Also, we assume that the behavior over the length of the member and also the loading conditions are constant. And also because we only use one strip over the length of this element to represent this member, we can only investigate failure modes that are bow-shaped, or eigenmodes that are bow-shaped, so that have only one half-length deformation. But as we have seen in the in our shell model, there can be, of course, for our second model here with a length of 28 centimeters, we have also local buckling as decisive failure mode, and we have like two buckles over the length of the section, and this cannot be represented or investigated with the finite strip method as we have it implemented into our program. And that's why we should like keep in mind or assume that we not only have one curve for this local buckling with the bow-shaped deformation, but we have also like a similar curve that has its limit or its minimum at a multiple of the first critical member length. Here, the first critical member length was 14 centimeters, but at 28 centimeters, we have this a similar bifurcation load, just that we have a multi-wave local buckling in the web. And we have multiple of these curves, so we should take the minimum bifurcation load for local buckling or also for distortional buckling as a straight line in this dialog. And like if we compare this then with the signature curve, we get a feeling at what point or what member length global buckling gets like relevant again before we have local stability failure. This is not only a nice tool to get a feeling for which stability phenomenon can be an issue for my cross section. So depending on the member length that I'm modeling, it could be that I can directly see, okay, local buckling is not a big deal, and distortional buckling is not interesting for me. I'm in a realm where global buckling will cater the design. Or I could also say maybe, okay, I'm at a length where local buckling and global buckling could happen at the same time, and I need to take into account some kind of interaction between these stability modes. And also it has also a practical use. So for code form design within our steel design add-on, we use the distortional buckling curve evaluated on the basis of this finite strip method to evaluate the effective sections of our code formed section. So we directly would use this minima, the second minima of this distortional buckling curve in the design of code formed members according to Eurocode 3 part 1.3, and also for code formed design according to the American standard, the direct strength method. So it has also a practical use and is already implemented in the code formed steel design. All right, that's it for the second topic, the cross-sectional design. The two last topics will hopefully not take that much time to explain. I just want to mention as a side note that we also can perform the linear eigenvalue analysis within our steel joints design. To demonstrate this, I have here a relatively easy model where I have a connection between a secondary member to a main member here. And the secondary member is loaded, and like I can not only do the usual steel joints design checks, but I can also perform a buckling analysis. And I first want to show you where I can activate it. You can find that in the ultimate configuration for the steel joint, and in the first point, perform buckling analysis. And if you have activated it, then not only the like resistance of the components is calculated, but also linear eigenvalue analysis is performed, and we can assess the results via the table. Here we also see that we don't only have the result values for the stress strain analysis, but also for the buckling analysis. And now in this table again we get the critical load factor for our 4 mode shapes that were calculated by default, and we can also assess the mode shape or analyze the mode shape by clicking on one of those table entries and opening the steel joints deformation or results button. And now I would see the mode shape for mode shape number 1 in this particular joint. I can browse through the different mode shapes by clicking the different table entries, and I can see that for this particular joint in the first mode shape, I would have some kind of web buckling under the load introduction here from the secondary beam. And yeah, then of course I could take some measurements to avoid that, but of course I need to also take into account the critical load factor in order to judge about how critical is this mode shape that I'm seeing here. We see that for the critical load factor of 11.8, we get this little warning sign here, and this just means that the critical load factor calculated is lower than the default limit value, which is 15. But that doesn't necessarily mean that we have a problem here. So the default bifurcation factor limit is derived from Eurocode 3 part 1.1, which is more for member design, and should be, this limit of 15 should be conservative for most of the cases. But what I would suggest is to really study the mode shapes that we observe here in the as a result of this buckling analysis, and then see if we can maybe extract limits for this critical load factor from the respective parts of the design codes. So in this case, as I said, we have some kind of web buckling under the concentrated load introduction here. So I would check chapter 6 of Eurocode 3 part 1.5, where this web buckling under patch loading is treated, and see if I can maybe derive limit values here. If I know which would be the correct limit value and I want to do something or improve the behavior, I can of course directly do that by modifying my joint. So I have also a second configuration of this specific connection, where I just added a stiffener in the main beam, and we see that the critical load factor for this configuration is has already increased from 11.8 to 17 just by adding these stiffeners to the main member web. And if I observe or study the first mode shape, I see that my like buckling panel is now divided by this stiffener. So every change has directly affects the results of this buckling analysis. Okay, then let's move to the last point. I promised to also show you how we can use the structural analysis model add-on to troubleshoot when we have some instabilities within our model. So I prepared another industrial hall. It's very similar to the third model, but here I reduced the number of load cases a bit, and I worked with load combinations, and I introduced some mistakes which lead to an unstable solution. So for example, I would have now modeled all my structure, I would have put in all my load cases, and now I would like to press on calculate and grab a coffee and enjoy that my model is calculating for me and doing all the computer is doing the rest of the job. But now I already see when trying to calculate the first load case, which is just the self-weight under first order theory, I get some warning message, and the program is highlighting that the stiffness matrix is singular, and I have some problem. It also highlights or gives a hint where I could look for possible mistakes, but I can't really see anything wrong here. I could now activate my structure stability add-on and apply or conduct an eigenvalue analysis with a specific setting, which is this one here. So in this case, when I want to check for instabilities, I can say that he should calculate eigenvalues without loading for instability checks. So he would look for, eigenvalues of 0 value and calculate the respective eigenvectors. And what I see now is that it seems like the girder in axis number 4 is more or less falling down. It seems like it's not connected to the beam. And when I zoom in here, I see, okay, there are 2 separate nodes, and the column is not properly connected to the girder, which could be, of course, the reason for my instability. So I just quickly resolve this issue and now try again to calculate load case number 1. Let's see if it works now. Again, I get an error message, and again I can try to get additional information with my structure stability analysis. So when I click here through the results, deformation results, I see that now for the rotations around the global x-axis, something looks a bit off. I get very, very high deformation values, and it seems like the girder here in the last frame freely rotates and is not, which indicates that it's not properly connected to the columns as well, or something. Some degree of freedom is not restrained properly. And if I look into the definition or in the connection, I see that I have a hinge on every column, on every column end, and I I defined this hinge with rotations, or I set free all the rotations in all 3 axes, which means, of course, this member can freely rotate at the top. So maybe that was a mistake, and I wanted to establish frame action here, but I just applied accidentally the hinges to all my columns. I can, now that I found this mistake, remove those hinges in the frame corners, and now check a third time if the solution runs or if the simulation works. And if I haven't done anything wrong, it should work now. Okay, now I get results for this first load case in my static analysis, which means that my model seems to be stable now. And now I want to go to the fullest and calculate all my load cases and load combinations. That would be the second stage, and it is again like not clear that I have no problems with my model, because my load combinations now I solve them with or I calculate them with second order theory. And I again get only for some load combinations errors that my swiftness matrix is singular and my structure is unstable. So this message can have two reasons. Either I have done something wrong in my modeling and I've connected, I have disconnected parts, or some DOFs are free and not restrained in my model. Or it could mean that my system is really overloaded because I have now calculated according to second order theory. It could also be that I have I've reached the critical bifurcation load of my system. And in order to check this, I would recommend to go to the load combination that is problematic. For example, in this case, load combination 5 or 2. And I can just switch to first order theory and calculate or perform a linear stability analysis, just a regular one. Now I just use the second setting where I calculate 10 eigenshapes. Could have taken less because I'm only interested in the first mode shape. And let's go to the results for my load combination 5. And what I can see now is that my critical load factor is below 1. And that indicates that my structure is indeed unstable because it is overload. And I can also check like what could be the issue based on the mode shape. And if I now look closely, I see that in my second frame, I set the wrong columns. I set the columns from the end frames, which are much too weak for these internal frames. But this can also be quickly resolved by just copying and overwriting the member dimensions with the columns from frame number 3 or 5. And if we now again perform the same simulation on our load combination 5, we will hopefully be able to get a suitable solution and a stable model. And now we can see, okay, with our first mode shape or critical load factor, we are above 1 and our model is good to go, and we have good chances that we can properly design the members within our structure. Yes, these were my last words. As I have announced at the beginning, it took me way longer than the 1 hour. I appreciate for that. I not appreciate. I excuse for that, and I hope it was nevertheless you learned something. It was not pure torture. And with this being said, I want to give the word back to Andreas Hörold for the outro. All right, for those that are still around, thank you for your attention.
Okay, thank you, Jonas, for this presentation. Yes, we are a little bit over the time, but I would like to show you, because I promised it in the chat, that I show where you can find the recording and the models. Just a moment, I take over the screen. So you can see our website, dlubal.com, and under news and events, you can find the webinars. Those are the webinars of the next weeks. Next week, the interface to Tekla structures, then our regularly, most frequently asked questions webinar, then steel member design for the USA. The building model add-on will be introduced, and so on. I scroll down to today's webinar because it's already accomplished. It's the reason why it's below. I click on it. So, and you will get an email in the next days with your attendee certificate and a direct link to that page. And then you will find the recording in the middle. The PowerPoint slides will be here. And you can already find the models to download. Those are the models of today's webinar. Okay, that should be also all from my side. Thank you for your attention. Thanks to Jonas for this presentation. Thanks to Sonja for the help by answering the questions. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.